Hello guys, how are you doing? I'm Mohammad Sadri, postdoctoral researcher at Electrical Engineering Department of TU Kaiserslautern, and I have titled this video using a DRAM controller on the ZYNQ PL for ZC706 board. And the reason I'm creating this specific video is I have seen several people, they need this, and they have some problems. They are trying to solve some problems using the ZYNQ device, in which they need a very massive amount of in fact memory bandwidth, and the memory controller that is there on the ZYNQ PS and is being used by default, that guy is not providing enough bandwidth for the type of memory intensive applications that these guys have. And on the other hand, there are some latency issues because you want to go from the PL in fact to the DRAM controller on the PS and then to the DRAM and then come back. And if you can have your DRAM controller directly on the PL and then perform transactions directly to this DRAM controller, then maybe you can have also smaller latency. So here comes the ZYNQ architecture. You have seen before this 1000 times, and in this architecture we have the DRAM controller on the PS, and this DRAM controller is usually connected to a DDR3 DRAM memory, and the data bus width is 32 bits. So you have a kind of theoretical total bandwidth of 4.2 gigabytes per second using this DRAM connection here. And practically what is happening is that this DRAM is being shared by the ARM host that you have here, and also the rest of the components and the rest of the logic accelerators that you have on the ZYNQ PL. And well, sometimes maybe it makes sense for some specific applications that you have accelerators that need large amount of memory. Maybe it makes sense to have a separate DRAM channel and a separate DRAM controller directly on the ZYNQ PL, and then to connect this DRAM controller to an off-chip DRAM memory, for example a DRAM module, and then to provide enough bandwidth and space for the accelerators to use this memory for the specific processing purpose. This is what the ZC706 board provides. So if you have watched the videos of lesson 8, you have seen that on the ZC706 board we have practically two separate DRAM modules. One is connected to the ZYNQ PS and the other one is connected to the ZYNQ PL. And the one that is connected to ZYNQ PL, since it has a data bus of 64 bits, it can provide practically higher bandwidth than the one which is residing on the ZYNQ PS. So what we are going to do in this video is to show how for the ZC706 you instantiate this DRAM controller here on your PL. And I'm just showing an example design, a very simple example design, in which I use this DRAM memory to share data between the hardware accelerators that you have on the PL and the ARM host that you have on the PS. So overall, if we want to look at the architecture of a DRAM controller, we will see something like this. Your DRAM controller basically, I can say, contains three parts. The first part is the Axon interface. So through this part, in fact, the DRAM controller or this whole module is providing an Axon slave interface through which different Axon masters can perform transactions to the DRAM memory. So you have the DRAM module here, which is outside the FPGA, and then you have your entire DRAM controller. And the DRAM controller, the first part is the Axon slave plug, and then the other part is the one who is doing the main, in fact, scheduling of read and write operations based on the incoming Axon transactions. And then finally you have the logic and the circuits which are talking directly to the DRAM module or the DRAM chip. That usually this part we call the PHY. It's a kind of physical interface through which you are talking to your DRAM memory and to your DRAM module. And then you have the memory controller, which is kind of intelligent part of your memory controller. This intelligent part of this whole block is this memory controller, and is doing, in fact, a scheduling of read and write operations and kind of producing required commands, required sequence of commands which should be applied to the DRAM chips that you have here, so that you can successfully write data to your DRAM chips and read data from them. And then you have your Axon slave plug here, which is usually connected to an Axon interconnect, and then to this Axon interconnect there are connected a set of Axon masters which are producing basically Axon transactions. So now I go to, in fact, VValue Environment, and I begin creating this simple design example. Before that, it's maybe interesting to see the DRAM module that we have on the PL part of the ZYNQ. This is the, in fact, the DDR3 SDRAM SODIMM. This is the in fact component that you have, the SODIMM component which is connected to the ZYNQ PL, and these are the specification, is the speed of this device, and basically this is this one, the one which is provided with the board is this one, and this is the fastest among all of the available options for this module. This is the fastest, but honestly speaking, I think by default, when you create your circuit, by default it is operating at this clock frequency, at this rate, at this transfer rate. And maybe you can really push the speed of your circuit to higher transfer rates, but I'm not sure, of course, but I feel this is the one, this is the real transfer rate that we have. We have 800 million transfers per second, which is of course a lot, with a data bus width of 64 bits. Yeah, so this is something I'm not sure about, but from the numbers that I see in this design of Xilinx, I feel it's operating here by default. Okay, let's go to the VValue environment. So I have the VValue environment. I have created this specific project for ZC706 board, and if you are receiving another board on which you have DRAMs connected to the PL, then with the board you should also receive the kind of board support package which contains the required files that VValue should use to also in fact customize the DRAM controller for that specific board. I will show this one to you very soon. So I create the block design. So here is the block design, and here we are adding the ZYNQ PS. It's usually the first step we do. Okay, this is the ZYNQ PS, and usually we run block automation for this. And with the block automation that I'm doing, practically I'm connecting this ZYNQ PS to its respective DRAM memory, which is outside of the chip. And now what I do, I want to instantiate, in fact, this component that I showed you here. I want to instantiate this DRAM controller. In order to do that, I use the, in fact, memory interface generator core of Xilinx. So I add another IP and I search for MIG, which stands for memory interface generator. So okay, I have now MIG for 7 series FPGAs of Xilinx. This is the memory interface generator, and actually you can very easily customize this guy for ZC706 by running block automation. So block automation, MIG 7 series, and in fact the device that we will have is DDR3 SDRAM. I just press OK. Okay, now for this guy to operate correctly, it needs a clock. The clock is different than the F clock that you have here. Is practically coming from the board. So if you look at the documentation of ZC706, this is the documentation of the Z706 board. I have it here. Maybe I show you the first page of this guy here. The first page. Sorry. Yeah. Okay. So we have this user's guide, and in this user's guide we have this section, DDR3 SOD memory, and this is introducing the DDR3 SOD memory, which is resided on the PL. It is introducing to you the part number and the data pass widths, and it says the data rate goes up to 1600 mega transfers per second, and this is actually what we see in the data sheet, but I'm in doubt if we are reaching this number. Anyway, these are the descriptions, and then we have here the clock generation section, and these are the clocks that you have on the ZC706 board, and this is the guide. This is the one which is going to be used for this new DRAM controller. It's called system clock. So have a look. It's system clock. It is differential. It's differential, and what's the clock frequency for this guy is 200 megahertz. So sorry, a 200 megahertz clock is entering this system, and of course inside the system we have clock multipliers. So this 200 megahertz clock will be multiplied by 2. It will go to 400, and as far as I know, this 400 clock will be used by the PHY. So if this is the case, and if the PHY is using a 400 megahertz clock, then the maximum rate that I see is 800 mega transfers per second, not more. So I don't know. This one I don't know. Okay, anyway, we have this guy here, and the other thing that I need to do is to connect this system reset to the reset, to one of the reset inputs of the board. So run connection automation, sys reset. I make this connection. Yeah, this connection is also down. So for now we have two components, and now you have your, in fact, DRAM controller here on the ZYNQ PL. What do you want to do with it? So this DRAM controller is providing you an Axon slave interface, and now you can instantiate your Axon masters in the ZYNQ PL, and the Axon masters can get connected to this Axon slave interface, and then through this interface they can directly write to your DDR memory and read from it. So for now, as an Axon master that I want to put here on this interface, I use the MicroBlaze core. I think this is the most flexible Axon master that I can use right now. So I add the MicroBlaze core to the story MicroBlaze, and then for MicroBlaze, of course, we run block automation. And for now, I want to configure the MicroBlaze in its simplest operational mode. So for local memory, the memory which will keep, in fact, the program that MicroBlaze will be running, I select an area on a memory of 64 kilobytes. And for now, let's forget about the caches of the MicroBlaze. For now, suppose that the MicroBlaze doesn't have any cache, and practically this is the only memory that is using for running the program. Okay, and for simple applications, this is kind of usually enough. And so the peripheral Axon port, I keep it enabled, and for the clock that is driving this guy, then we have several options. Okay, so here if I look at my MIG 7 series, at my memory interface generator, is also producing for us a clock, and you can use this clock for the blocks that are going to talk with this MIG 7 series. So here I can select this guy, which is basically the clock which is produced by this MIG 7 series, or I can select this guy, and then later, since we have the Axon interconnect between the MIG and the MicroBlaze, the Axon interconnect will take care of converting from one clock domain to the other. But for now, I will select this one. I will press OK. Okay, now here we have the kind of system. We have the MicroBlaze. The MicroBlaze is connected to its program and data memory. And then we have this MAXA DP port is not connected to anywhere yet. This is the, in fact, debugging interface. And later, if I connect to the board with XMD, I should be somehow able to get connected to this one and debug the MicroBlaze board. We have the ZYNQ PS here. Practically, it is not playing any role right now. And then we have the MIG core, and we have now used the output clock and the output reset signals of the MIG core to drive the logic that I have on the PL. Okay, now I go ahead one step. What I want to do, I want first this guy to be able to perform write transactions to this Axon slave port and to perform read transactions. So run connection automation, and for this Axon slave port, I want to make it connected to the MicroBlaze. So here we go. We have the MicroBlaze. We have the, in fact, let me zoom in a little bit. We have the Axon master port. We have an Axon interconnect. Practically, the Axon interconnect right now is being completely driven by the clock signal, which is produced, in fact, by the MIG core. Okay, and so this guy, this Axon master port, comes to the Axon interconnect, and then the output of the Axon interconnect is connected to this MIG7 that we have here, and I believe this connection should work, and we should be kind of able to do transactions from the MicroBlaze to our DRAM memory, which is connected to the PL, and to write data to it and to read data from it. But what I want to do is a little bit more. I want the ARM host that I have here also be able to perform transactions to the DRAM memory that I have here. So I want to use this DRAM memory as a kind of buffer to share data between the MicroBlaze core that I have on the PL and the ARM host that I have on the PS. So what I do is simple. I again come to run connection automation, and now I have this GP0 port, which is an Axon master, and then I want to connect this Axon master to this Axon slave, right? So let's just press OK. Yeah. Now what's happening? What's happening is that this GP0 port is coming to the same Axon Interconnect that we were using for connecting the MicroBlaze to the DRAM controller, PL DRAM controller. And what's happening for the clock, what we see here is that the clock for the GP0 port is practically coming from the MIG. So this clock is now driving the whole system, and I think in terms of synchronization this is completely fine, because the same clock is driving all of the clocks of the system, and then inside the PS there is the shift from this clock to the internal clock domain of the PS. So I think for now we don't need to be worried about this. One thing that I should emphasize is that I have not yet tested this design on the real board. Of course I will soon do it, but I decided to create this video, and then later if it needed any change I will create another update video. But I think this is showing this concept and how we are doing this thing. So now if I look at the design, I think it is kind of complete. We have MicroBlaze, we have ARM host, they are sharing memory. This memory is on the PL of the ZYNQ device. So if you remember, and if you have seen what we have been doing so far, we have the memory here, and we were using this memory to share the data between the ARM host and the accelerator that you have on the PL. And what we are doing in this video is different, because we are using the DRAM memory on the PL of the ZYNQ device. Instead of the DRAM memory on the PS, we are using the DRAM memory on the PL of the ZYNQ device to share the data between the accelerator and the ZYNQ device. Okay, I think the design is kind of complete. The interesting part of this story is now the address editor. If I open the address editor, practically we have two CPUs, and each of these CPUs, they have their own address space and they have their own slaves. Yes, so here for this CPU I have just one slave, that's practically this DRAM controller, which is residing on the PL. This is the address range. And for the MicroBlaze we have, in fact it's two program and data memories, which are operating based on the LMB bus of MicroBlaze, and then we have also the DRAM controller as one slave. Yeah, I feel if I change this one back to 4 is better. I want consistent address between these two, because eventually they are sharing this interconnect, and this interconnect has a kind of logic for decoding the address. And I want just to be sure that the interconnect always sees this memory in a specific fixed address range. So yeah, there are a lot of stories here. For example, you may ask, what if I wanted to use different addresses for these two parts? It's possible. It's not a problem. But for now, let's keep them the same. Or you may ask a lot of other things. For example, you may ask, what if I wanted to change these addresses on the fly? I mean, up to now we have some addresses, and from now on I want to have another addresses. Yes, again, this is possible. Not this interconnect that you have here, it has a fixed address decoding logic, but it's possible by adding suitable interfaces here. But for now I don't think we need that. So here is our design. I save it, and let's just create HDR wrapper. I make sure this thing is fine. Okay, now then you go through the rest of the steps of the design. Of course, you go to generate output products, then synthesis, implementation, and you generate the bit stream. Yet there's an interesting point. When you generate, in fact, a bit stream, you reach the step that you export your hardware to the software development kit of Xilinx, and you begin developing software. And this is a kind of different than what I have been showing so far, because so far we had just one CPU in the system. It was this ARM host. And now when you export your hardware to the software development kit, in fact you are exporting hardware which contains two CPUs, and each of these CPUs, it has its own separate tool chain for compiling the applications, which is different than the other. And it's kind of time consuming, because I should do up to generate the stream to show you this part. But as of what I have done, VValue handles this situation very well, so you will not have any problem. When you open the software development kit, you will have a kind of environment like this. I think this is remaining from the previous test that I have done. And here is the description of the system. VValue recognizes both of the CPUs very well. So it recognizes you have in your hardware the MicroBlaze, and it recognizes you have in your hardware the, in fact, ARM Cortex A9. So both of them will be recognized. And then here, when you in fact begin writing your application, you can of course select on which target this application is going to be executed. So here I have created a simple hello world project for the ZYNQ, for the MicroBlaze device, and I have compiled this, and I have an ELF file which is the result of my compilation. I have hello.elf file, and this is basically for the MicroBlaze, and it should be executed on the MicroBlaze. Now if you remember from my previous videos, I showed you can use XMD to in fact load your ELF and then run it. And I think you can use XMD to do this for both of the MicroBlaze and ARM host, but I'm not sure because I have not done that myself. One solution that you can follow to in fact make the MicroBlaze run its respective code is to integrate the ELF that you have created inside SDK for MicroBlaze to integrate this ELF into the bit stream. The point here is that if we look at our design, we have this memory here, this program and data memory, which will contain the program that MicroBlaze is going to execute. And this program memory is small, and it will use, in fact, the block memories of the FPGA. So what I do, I integrate the ELF file that I have created for MicroBlaze into the bit stream. So I come here, I say add source, next add files, then I find the ELF file that is created by the SDK environment. So it's inside hello debug hello.elf. I add this guy to the story, and so now it's here, and then I associate ELF file, and I tell the tool that this ELF file is the ELF file which belongs to the MicroBlaze, and so should be copied on these block memories which are here, and use also this ELF file during both synthesis and simulation. So this block that you see here, that this it will not being shown to you if you generate output products. I have not done that because it takes a little bit time, but instead of this, you will see another window that will show you to who this ELF should be associated, and usually by default it is correct, so you just press OK. You don't need to change anything. So this is what you do, and you generate bit stream again, and then you should have inside your bit stream the contents, the correct contents of these memories. So you are not worried about the MicroBlaze part, because as soon as you load the bit stream to the FPGA device, the program for MicroBlaze is already loaded, and when the reset gets deactivated, the MicroBlaze will begin running its code. Okay, that is it for now. Yeah, I emphasize again, I have not tested this on the real hardware, but I think maybe in some days I will do it. Yeah, thanks for watching. Yeah, if you liked my videos, of course make a donation, because it will directly affect the quality of the videos, and I can try more things. I can show you more practical examples using better boards. So yeah, if you like, you can do it. Yeah. Okay, once more, I'm Mohammad Sadri, postdoctoral researcher, TU Kaiserslautern, Germany. Thanks for watching. Bye.